chat so that the speaker can respond to them. And we move on to the second talk by Jana from Graz University of Technology on calibrating school models to cluster tracing data.
All right, let me share my screen. I hope you can hear me.
Yes, okay.
Perfect, and see my screen. Okay, well, thank you for the kind introduction and invitation.
Jana, I will let you know 5 minutes before you are to finish so that you know that how much time you have, okay?
Okay, perfect.
Sorry, yeah.
Yeah, I'm actually quite happy about the preceding talk because it introduced many of the concepts that I will also need in my talk, so I can be a bit quicker there. So my talk will be specifically about calibrating school models, such as the one as we just saw, to cluster tracing data to make sure that our models reflect reality as closely as possible. First of all, let me walk you through the basic components of the approach and the model we are working with. We are also using an agent-based model of SARS-CoV-2 spread in schools, which is composed of, first of all, a model of the infection in an individual, then a contact network model of the school or schools, to be more precise. On top of that, we can sprinkle a number of interventions such as wearing masks, regular screen testing, cohorting classes, or ventilation. And then, of course, there is the calibration step where we tune the parameters of our model such that it reflects the observations in reality as closely as possible. And this calibration step is what most of my talk will be about, but first let me go briefly over the other components so you can understand how it all works together a bit better. The model of the infection in the individual in our model is closely tied to kind of an approximation of the viral load in an individual. So we start out with a susceptible individual. At day 0, at the transmission, the individual becomes exposed, and as the viral load increases, the individual becomes infectious and then either stays asymptomatic or becomes symptomatic. And then again, after a few days, the individual recovers and ceases to be infectious. And since we want to incorporate quarantine in our model, we also have each of these states in a quarantined version where the agent simply doesn't have any contacts to other agents anymore. And the transition periods between these individual agent states are drawn from distributions for these epidemiological parameters, which we know, thankfully, from literature for the various virus variants that we're dealing with. Now, the contact networks of our schools, we actually did not have empirical data for that for schools in Austria. I was quite happy to see that this exists in France. We nevertheless found a workaround to still come up with proper co-location networks in our schools. We made use of the fact that schools are highly organized environments that have kind of laws and timetables governing how they function. And we used information from the National School Statistics of Austria that gave us information on the average class sizes for different school types, the average number of classes, and the average number of teachers, as well as teaching timetables to figure out how many different teachers are teaching a given class. And then we also conducted a series of interviews with teachers and principals to kind of make sure that our assumptions about how this contact structure in the school looks like are based in reality, and also to adapt for any changes that might have happened due to how they were dealing with the pandemic. So what you can see here is the agents in our model. In red, the students organized in these circles, which symbolize the classes, and in blue, the teachers. And then we add contacts to all these nodes based on the reality in the school. So based on all the different interactions that happen in the school that cause two agents to have a contact with each other. For students, we have 3 types of contacts. First of all, we have siblings. We chose to include this specifically because in Austria, schools really go to great lengths to enable children from the same household to go to the same school if it fits age-wise. And these contacts are household contacts, so the transmission risk is probably quite high there. And these are contacts that would enable a transmission to jump quickly between classes, so we explicitly incorporated those. Then, of course, students can be classmates and have a contact there. Students can be daycare mates. These are all the orange connections that span between classes, because we learned to our surprise that even under pandemic conditions during daycare, classes were mixed. They were not kept in the class groups. So this caused a number of connections between classes as well. Then teachers obviously also have contacts amongst each other, either through, for example, jointly teaching or supervising a group of students, being acquaintances next to work, or just having work meetings. And then on top of that, there are all the connections between teachers and students, which are caused by a teacher teaching a class or supervising a daycare group. Now, what I show you here is a contact network of a typical Austrian primary school with afternoon daycare. It has 8 classes, and every class has on average 19 students. This, for comparison, is the contact network of an average Austrian secondary school. And you can appreciate that it looks very different. First of all, there are way more students, way more classes, way more teachers, and way more contacts between teachers and students, because several teachers are teaching the same class, whereas in primary students, only one teacher is mostly teaching a given class. And this already hints at the necessity of modeling school types with different contact networks to kind of appreciate the organizational differences in the different school types. So in summary, we model a total of 6 different school types, which are the most prevalent school types in Austria. We have primary schools for students aged 6 to 10, also with afternoon daycare, then lower secondary schools for students aged 10 to 15, again with daycare, upper secondary schools for children aged 15 to 18, and then the secondary schools for children aged 10 to 18. And due to our education system, these school types kind of coexist with the upper secondary and lower secondary schools. Well, and each of these school types is quite different in terms of the average number of classes it has, the average number of students per class, and the average number of teachers. And this is incorporated in our contact networks. All right, now to simulate how the infection is transmitted or spreads throughout the school, we basically have to answer 3 questions. First question is, do agents meet? Then, is one of the agents infectious? And the last question, whether there is a transmission between the agents or not. The first question is answered by our dynamic contact network. And I say dynamic here because the contact networks I just showed you depict a weekday, and during weekends, we remove all the contacts that are caused by the school, and we only keep the household contacts. Then the question of whether one of the agents is infectious or not is answered by the dynamics of the infection in the agent itself. And to answer the question of whether there is a transmission or not, we perform a Bernoulli trial with a probability P of an infection happening, which is modified by a number of parameters. Now let me dig deeper into this, because this is where the magic happens. This is also where we need to start with our calibration. So what you see here is the equation for the probability P of a transmission happening. We have so-called base transmission risk beta, which is equivalent to the household transmission risk between 2 adults, which is then modified by a number of other parameters, which are the Q's in this equation. We have a modification, a reduction of transmission risk due to a contact being a school contact. We assume that it's likely to have a lower transmission risk than a household contact. Then we modify the transmission risk based on the age of the transmitting agent and the age of the agent being infected. And then we have a modification due to infection progression. So we assume that agents are more infectious at the beginning of the infection, and then progressively the transmission risk decreases. And we also have a modification depending on whether the agent has symptoms or not. Asymptomatic agents have a lower transmission risk. Now, the last 2 modifications we can thankfully take from the literature, but the first 4 parameters are free parameters in our model and need to be calibrated so our model reflects what happens in reality. Now, before I dive into how we perform the calibration, let me quickly introduce you to the data we used to calibrate. Thankfully, we got a quite fine-grained data set of clusters, outbreaks that occurred in Austrian schools by the Austrian Agency for Food and Health, the AGES, and which produced these cluster tracing data in cooperation with the local health authorities. We have a total of 536 clusters over different school types with a bit over 3,300 cases. And for every infection case in every cluster, we know the age of the infected person. For every cluster, we know the source case. And for every infected person, we also know whether or not they were asymptomatic or not. And then we group these clusters, we assign them to the different school types based on the age of the involved agents. So everything that involves only adults and children under 10 years is primary, and lower secondary, upper secondary, and secondary. And everything that couldn't be assigned to a school type based on one of these rules, we label otherwise inconclusive, and we don't use these in the further calibration, but I still report them, the numbers here. All right, from this we can work out the cluster size distributions for the different school types. We can see that for primary, lower secondary, and upper secondary schools, cluster sizes are on average smaller, whereas for secondary schools and also this inconclusive share of the clusters, we get comparatively much larger outbreaks. And this distribution of cluster sizes is actually one of the two main things we're going to calibrate our model to reproduce these cluster size distributions. The second type of information we get from this data is the share of student source cases, so who actually introduced the cluster into the school. That you can see to the left, and we can see that for primary schools, there's almost no students introducing the infection into the schools, almost all teachers, whereas for upper secondary schools, it's almost all students that introduce the infection into the school. And the same information we have for the share of students that are infected in each cluster. And here we can see that in primary schools, only about 3/4 of the cases in every cluster are students, whereas for the upper secondary and secondary schools, almost all infections are students. And the fact that students are so overrepresented here makes a lot of sense, because the schools have just way more students than teachers, obviously. And this share of students that are infected in each cluster, this is the second characteristic that we're going to use to calibrate our system. And then we also get the ratio of asymptomatic cases in each cluster, and starts out about 3/4 of children aged below 6 years are asymptomatic, whereas when we are in the adult age range, this drops to about 1/4. And these numbers are comparatively low to what we know for asymptomatic infections of COVID. This is all wild type strain. And this is, I think, explained by the fact that the cluster tracing mechanism that Austrian health authorities employ actually have follow-ups. So they will identify people who were pre-symptomatic when the first contact to the health authority happened, and they exclude these pre-symptomatic people that later became symptomatic in the statistic. So this really is only asymptomatic people, not pre-symptomatic. All right. And then the last piece we did in the puzzle to calibrate our model is the conditions that we actually had during the time of data collection in schools. So this data was collected in autumn 2020. We had a basic test trace isolate protocol implemented in schools, where when an infection was detected, the infected person was immediately isolated, and all the close contacts were quarantined. Namely, I think it was table neighbors, and in some cases also students, teachers that had a closer contact to the student. And then a thing that was kind of a bit special about Austria, and which I think also makes this data very valuable, is that there was rigorous testing of all the K2 contacts. So all the students in the same class and all the teachers that had contact with the students were tested. So we think that there is not that much bias in that asymptomatic children were not detected, because we had this wide cast net of testing around an infection case. Then there was no mask mandates implemented in schools at the time yet. There was no additional ventilation and no preventive testing or class cohorting either. And there were strict measures to prevent mixing between classes, such as staggered start times and kind of walking protocols in the hallways, which was even more mind-boggling given the fact that the classes mixed during daycare, but apparently that didn't count. We were puzzled by this, but the teachers confirmed that in the interviews. And then, as I already said, during that time, the original strain was circulating. All right, now our aim is to use this information to build a model of infection transmission in schools that reflects this data that I just showed you as closely as possible. And then we want to use this calibrated model to test the effectiveness of additional intervention measures on top of that, similar to the talk you just saw, and I will just briefly touch on this in the end of my talk. So to calibrate the model, we kind of tried to drill or separate out the three parameters a bit to not have such a high dimensional problem that we needed to search. And thankfully, we could calibrate the household transmission risk, so this base transmission risk beta, independently of the other three parameters, because it only depends on infection progression and symptoms. And this we could take from the literature. It doesn't depend on any school-specific or age-specific modifications, because it's just a transmission between two adults in a household. And we know that the expected secondary attack rate in households for the original strain was about 38%. And so we just sample adult individuals, give them epidemiological parameters according to their distributions, and let them infect each other. And then we adjust the space transmission risk beta such that we hit this target secondary attack rate in households. And then we find that in our model, beta needs to be about 7.4% transmission risk per day of simulation, such that we will produce this secondary attack rate in households. Now on to the more complicated calibration task, the remaining three parameters, namely the modification of transmission risk due to a contact being a school contact and due to the age of the transmitting and receiving agents. This is more complicated because these parameters depend on each other. So we kind of need to vary them together to see the impact on the overall transmission dynamics in the school model. To make this task a little bit easier, we make one assumption. We assume that this Q2 and Q3, namely the transmission risk reduction due to the age of the transmitting and receiving agent, are the same, and they vary together. And we condense this into a new parameter, which we simply call QH. And we also make the assumption that this dependence on age is linear and decreases with every year that a child is younger than 18. And now to calibrate the system, we optimize an error term, which is kind of the difference between what our system produces to the actual empirical data. And this error term is composed of two components. The first part is this difference between the cluster size distributions. And the second component is this difference between the share of infected agents. So how many students, how many teachers are infected in a cluster. We weigh this by the number of empirically observed clusters for every school type, and we sum over the different school types. And this is the overall error that we are optimizing. And then we perform simulations for all school types, where we draw source cases from the known distribution of source cases between teachers and students. We use the known age dependence of asymptomatic infection courses, and we simulate with the known conditions in schools, namely only test, trace, isolate. And then I kind of consciously left this definition of difference between the observed and simulated characteristics a bit vague, because we actually tested different difference measures. We didn't want our outcome to be dependent on the specific difference measure that we used. So we tested the sum of squares, chi-squared distribution difference. Bhattacharya, Spearman, and Pearson correlation, and also the difference of a fit to the QQ and PP slope to 1. And I kind of made sure that all these different distance measures converged at a kind of similar point. And these heat maps that you can see here is simply varying this contact modification for a school contact and the age modification together. And for each of these parameter combinations, we performed 4,000 simulations. And then we could determine the minimum in this plot. And as you can see, these plots are still a bit noisy. So we bootstrapped these ensembles of simulations 1,000 times to kind of get a confidence interval around the minimum. And this is what we find. So we see that for all the different distance measures, we kind of get a convergence of this contact modification at around a third. All of the distance measures confidence intervals overlap. We eventually decided to go for the sum of squares as a distance measure, and same picture for this age modification, where we also see that the difference measures give us kind of similar results. We also picked the sum of squares for the sake of simplicity. And so the final outcome is that the contact rate is about 0.3, which means that a school contact is the transmission risk for a school contact is about a third the transmission risk of a household contact. And for the age dependence, we get minus 0.005, which means that per year a child is younger than 18. The transmission and infection risk is reduced by about 0.5%. So a child that is 6 years old will have a 6% lower transmission risk than a child that is 18 years old, which is not that much. All right, I see that I'm almost out of time, so I will quickly brush over these. What we then did with this model was very similar to what you just saw. We tested different intervention measures, preventive testing, masking, ventilation, reduced class sizes. And we could see for every school type, we could get these outbreak distributions depending on who introduced the infection to the school. And then we could put different measure combinations on top of that and see how the outbreak distributions developed. And then we made a recommendation for measures that were needed in different school types to kind of control the outbreak sizes, keep the average reproduction number below 1. And these measures were then actually implemented in Austrian schools. This was now only relevant for the Delta period. These results are for Delta. But yeah, that was quite nice that we could find some very actionable results that were then also implemented. Yeah, same for secondary schools. The main outcome here is that secondary schools need more measures than primary schools because there are more contacts there. It makes a lot of sense. And that for Delta, at least, a combination of 3 different measures was sufficient to control outbreaks in secondary schools, whereas in primary schools, you only needed 2. And that's already it. This is the collection of materials. We have one publication about the school study in Nature Communications, and the second one where we used the same calibration, but this time for spread in a university contact network, which was just accepted yesterday. And I also want to thank the team that contributed to this, Peter Klimek, first and foremost, who is also here today. There's a simulation package associated with the simulation that is free to use. Data is also open. And if you're interested, the slides are here, and I also posted them in the chat. Thank you.
Well, thank you very much, Jana. Maybe we have time for a couple of very quick questions. And I do not see any questions in the chat. Maybe I can ask you a question. I'm a bit ashamed. I think like all your talk was about estimation, and I did